Hello, and welcome to this course. We are excited to have you join us and look forward to supporting you throughout your learning journey. Before you get started, please take a moment to carefully read the following message. Once you have finished reviewing the information, simply click the button below to continue. Thank you for your attention, and we hope you enjoy the course.
Introduction to Capacity Requirements Planning. Capacity Requirements Planning, CRP, is a crucial manufacturing planning process that translates the Master Production Schedule, MPS, and Material Requirements Planning, MRP, into detailed capacity needs for work centers. Its primary purpose is to ensure that sufficient resources, both labor and machines, are available to execute the production plan. By doing so, CRP helps prevent bottlenecks and ensures that production schedules are realistic and achievable. CRP differs significantly from rough-cut capacity planning, RCCP, by providing a much more detailed, operation-level view of capacity. While RCCP assesses capacity at a higher product family level, CRP delves into individual work orders and specific work centers. This detailed analysis allows for precise identification of overloads and underloads, enabling proactive adjustments to the production schedule. Core concepts: capacity, load, and time buckets. Understanding core concepts like capacity, load, and time buckets is fundamental to effective CRP. Capacity refers to the maximum output a work center can produce in a given period, considering available machines, labor, and working hours. Load, conversely, is the total amount of work assigned to a work center, expressed in standard hours or units derived from planned and firm orders. Time buckets are discrete periods, such as hours, shifts, days, or weeks, into which capacity and load are aggregated for analysis. The choice of time bucket granularity depends on the level of detail required for decision-making. Accurate data regarding routings, standard times, and resource availability is paramount for reliable CRP results. Key inputs for CRP calculations. Accurate inputs are essential for generating reliable CRP results. Key inputs include work orders, which detail the quantity and due dates of items to be produced, encompassing both planned and firm orders. Routings specify the sequence of operations and work centers required for each product, along with standard times for each operation. Other crucial inputs involve available hours per work center, which account for shift patterns, breaks, and maintenance schedules. Resource calendars provide detailed information on the availability of specific machines and personnel, including planned downtime and holidays. These data points collectively form the foundation for precise capacity calculations. Calculating required work center load. The process of calculating required load involves converting order quantities into standard time demand for each work center. This is achieved by multiplying the quantity of each item by its standard time per operation, as defined in the routing. These individual operation demands are then summed up for each work center within specific time buckets. Once the total load for a work center in a given time bucket is calculated, it is compared against the available capacity for that same period. This comparison immediately highlights periods of potential overload or underload. Accurate load calculation is vital for identifying where capacity adjustments may be necessary to meet production targets. Building capacity profiles and load charts. Building capacity profiles and load charts provides a clear visual representation of resource utilization over time. A capacity profile illustrates the available capacity of each work center across various time buckets. Load charts, on the other hand, plot the calculated load against this available capacity, often cumulatively. These charts help visualize utilization rates, showing how busy each work center is projected to be. More importantly, they quickly highlight periods of overloads where demand exceeds capacity and underloads where capacity is underutilized. This visual insight is critical for making informed decisions about resource allocation and scheduling adjustments. Identifying bottlenecks and constraints. One of the primary benefits of CRP is its ability to clearly identify bottlenecks and constrained resources. Bottlenecks occur at work centers where the required load consistently exceeds available capacity, creating a choke point in the production flow. These are visually evident as significant overloads on load charts. Identifying these constraints allows planners to focus their attention and resources on alleviating these specific points. Understanding where bottlenecks exist is the first step towards implementing targeted improvement actions, such as capacity leveling, overtime scheduling, subcontracting, or reassigning work. This proactive approach prevents delays and optimizes overall throughput. Finite versus infinite loading techniques. CRP employs two main loading techniques: infinite loading and finite loading. Infinite loading assumes unlimited capacity and schedules all work orders, based purely on their due dates and routings, without considering actual resource availability. This method is simpler, but often results in unrealistic schedules with significant overloads. Finite loading, conversely, acknowledges actual capacity constraints and schedules work orders only up to the available capacity of each work center. This technique uses sophisticated algorithms and heuristics to sequence jobs, preventing overloads, and generating more realistic, achievable schedules. While more complex, finite loading is essential for managing constrained resources effectively. Practical mitigation actions for overloads. When CRP identifies overloads, several practical mitigation actions can be implemented to balance the load. These include shift smoothing, which involves adjusting work schedules to distribute tasks more evenly across shifts, and work center balancing, where tasks are reallocated between similar work centers. Alternative routing allows for using different machines or processes if available. Other strategies include lead time adjustment, where due dates are negotiated, or split production, where large orders are divided among multiple resources. Subcontracting parts of the work to external vendors is an option for severe overloads, and applying priority rules helps ensure critical jobs are completed first. These actions help maintain schedule adherence and customer service.
Integrating CRP with MRP and NPS CRP is not a standalone process, but an integral part of a larger production planning system. Closely integrated with material requirements planning, MRP, and the Master Production Schedule, MPS. The MPS, which defines what products to make and when, feeds directly into CRP as the primary demand for capacity. CRP then validates if the MPS is achievable given current resources. Feedback from CRP is crucial for adjusting the MPS or taking exception actions. If CRP identifies persistent overloads, the MPS might need to be revised or capacity must be increased. This iterative process ensures that production plans are not only material feasible, but also capacity feasible, leading to more reliable and executable schedules. Time bucket selection and aggregation. The selection of appropriate time bucket size is a critical trade-off in CRP, balancing the need for detail with manageability. Fine granularity, such as hourly or shift-based buckets, provides highly detailed insights, crucial for short-term operational scheduling and immediate bottleneck identification. This level of detail is ideal for shop floor control. Conversely, coarser buckets, like weekly or monthly, are more suitable for strategic planning and long-term capacity adjustments. These aggregated views help in assessing overall trends and making decisions about major equipment purchases or staffing levels. The optimal bucket size must align with the specific decision-making needs and the planning horizon. Common CRP tools and templates. Various tools and templates facilitate effective CRP implementation. Simple spreadsheet load calculators are widely used for smaller operations, allowing manual input of data and basic capacity load comparisons. Gantt charts provide a visual timeline of tasks and resource allocation, helping to identify scheduling conflicts. More sophisticated finite capacity schedulers are software solutions that automate the loading process, apply complex algorithms, and generate optimized schedules while respecting capacity constraints. For daily adjustments, simple shop floor boards or digital displays can be used to communicate current work center loads and priorities to operators. These tools enhance efficiency and visibility. CRP governance and key performance indicators. Effective CRP requires robust governance and a clear planning cadence. This involves defining roles such as the CRP planner, production supervisor, and master scheduler, each with specific responsibilities in the planning and execution cycle. Regular review meetings are essential to discuss capacity exceptions, adjust plans, and escalate issues when necessary. Monitoring CRP effectiveness is achieved through key performance indicators, KPIs. Important KPIs include schedule attainment, which measures how well production meets its targets, and work center utilization, indicating resource efficiency. Lead time adherence, the number of emergency reschedules, and work in process (WIP) levels at constrained resources also provide valuable insights into the health and responsiveness of the planning process.
Thank you so much for completing this course. I hope the knowledge and skills you gained here help you reach your goals. It's been a pleasure having you in the class, and I'd love to see you in the next course where we'll build on this foundation, explore new topics, and tackle more challenges together. Wishing you success in your next steps. Keep practicing and stay curious.